Hey everyone, welcome to another video, and today we are going to be exploring the properties of Brownian motion as well as an introduction to stochastic calculus. So what is Brownian motion? First of all, let's start off with a simple experiment. So for example here, we're playing a game where if you flip a coin and you get heads, then we're going to move up by 1. However, if we get tails, we're going to move down by 1. So we keep playing this game repeatedly, and we're going to have a graph that looks something like this. So whenever we go up, that means we got a heads, and whenever we go down, that means we got a tails. So however, now we want to imagine this game, instead of having distinct time intervals, for example, t1, t2, we want to have the time intervals be continuous, as in we're constantly flipping with infinitely small time intervals. And correspondingly, we're not going up that much, we're actually going up as small as our time interval is. So with that, we're going to form a Brownian motion, and it's going to look something like this. So this might look like a stock diagram or the path of some instrument, and this is actually an example of a Brownian motion. So there's some main properties of a Brownian motion that we want to take advantage of later on to look at the problems. So some properties, first of all, a Brownian motion is continuous. There's no gaps, and there's no distinct time intervals, as in everything is happening continuously. And another property of Brownian motion requires us to take a look at its value at different time intervals. So for example, let's take a look at this time interval here. Let's call that t1. And this time interval, let's call this t2. So we want to know the average of what the Brownian motion is going to be, or the expected value at t1 and at t2. So the main property of a Brownian motion is that the difference between different time intervals, let's actually label this as t0. So bt1, b is the representative of a Brownian motion. So the difference between Brownian motion at t1 and t0 is going to be normally distributed, so a normal distribution with a mean of 0, and a standard deviation of the difference in time. So in this time, the difference is t1 minus t0. So we know that Brownian motions, we start at 0, so b0 equals to 0. That means we can get rid of this term, and we can get rid of this term. So what we have left is that bt1 is in a normal distribution. It's normally distributed around a mean of 0, and has a variance of t1. So now looking at the difference between t1 and t2 here, bt2 minus bt1, this is also normally distributed. This is the main property of Brownian motions, around a normal distribution, again, of a mean of 0, and a variance of t2 minus t1. So to picture this, we can say that the difference between t1 and t0 is normally distributed. So it looks something like a normal curve with a mean of 0. So on average, we're not going to change. And we have a standard deviation based on how long has passed. So now from t1 to t2, there's a slightly bigger time interval. So the variance is larger in this case, and we're going to have a normal distribution that looks something like this, with a larger variance than before. Let's actually draw that again. So this is the main property of a Brownian motion, in that it is normally distributed for every change in time intervals with a mean of 0, so on average it doesn't change, and with a variance of the difference in time, so t1 minus t0 or t2 minus t1. So let's start looking at some problems involving Brownian motions. So first, for problem 1, let's let B be a Brownian motion. So what is the probability that b1, so b at time interval 1, is greater than 0, and the probability that b2 is less than 0. So what's the probability that we have something that looks like this? It doesn't have to be exactly this, it just has to be that B1 here is greater than 0. Let's call this T1. It's just the time interval 1. And B2 is something less than 0. So at interval 2, we have something that's less than 0. So we need this probability. What's the probability B1 is greater than 0 and B2 is less than 0. So we're not sure how to actually calculate this probability. However, we can try to divide it into some probabilities that we do know based on the properties of Brownian motion. So the probability, let's just write this again. B1 greater than 0, B2 is less than 0. First of all, what's the very first thing? We need B1 to be greater than 0. So we know that B1 is normally distributed around a mean of 0 and a variance of t. In this case, t is 1. So what is the probability that it's in the top half or the upper half? So this half here, it's going to be 1 over 2. So there's a 1 over 2 chance that B1 is greater than 0. So let's just write that out. So B1 is greater than 0. So what else do we need? We also need the fact that B2 minus B1 is less than 0. In that case, so first we're talking about the going up trend here, calculating that, and then we're going to talk about the going down trend here. So what's the probability that B2 minus B1 is less than 0? Let's actually move all of this down so we have more space. So the probability that B2 minus B1 is less than 0 is the same thing as saying the probability that B2 is less than B1. So these things are identical, B2 and B1. So the probability that this is less than 0 is just 1 over 2 as well. So finally, we need the probability that the absolute value of B2 minus B1 has to be greater than the absolute value of B1. So basically we're taking the complicated question here that requires B1 to be greater than 0, B2 to be less than 0, and dividing that up into 3 different probabilities that we can actually calculate based on properties of Brownian motion. So first of all, we need B1 to be greater than 0, basically the increased up arrow here in green. Then we need B2 minus B1 to be greater than 0, to be less than 0, which is saying that after we reach time 1, we've gone down. And finally, we need this probability, so the absolute value of B2 minus B1, to be greater than the absolute value of B1, which is saying the degree that we went down is greater than the degree that we gone up. So the red arrow is greater than the green arrow in terms of magnitude. So immediately we know that the chance B1 is greater than 0 is 1 over 2. By symmetry, similarly, the probability that B2 minus B1 is less than 0, basically the probability that the red arrow is facing down is also 1 over 2. So now what is the probability that B2 minus B1, or absolute value, is greater than the absolute value of B1? So we can note that this probability here can also be represented by something like this. B2 minus B1 is greater than B1 minus B0. We omitted B0 because it has a value of 0, so it doesn't actually matter. But we can see that this here and these are both normal distributions with a mean of 0 and a variance of 1. So mean of 0, variance of 1. So these two are actually identical. And this is because of this property of Brownian motion that we have right here. The difference between two timestamps is always going to be a normal distribution with a mean of 0 and a variance of t2 minus t1. So because the difference in time is always 1 in both the left case and the right case, we know that these are two identical distributions. So what's the chance that one is greater than the other? Well, it's going to be 1 over 2. Because the Brownian motion is continuous, there's no probability that these two are identical or exactly the same. So one is always going to be greater than the other, and there's an equal chance either is greater than the other. So this here also has a probability of 1 over 2. So multiplying these three probabilities together, we have a probability of 1 over 8. So there's a 1 over 8 chance that at timestamp 1, we're greater than 0, and at timestamp 2, we become less than 0. So that is the first question that we're going to cover. So moving on to the second question, question 2, what is the correlation coefficient or covariance? So what is the covariance between, not correlation, it's the covariance between a Brownian motion bt and its square, and bt squared. So if you guys aren't familiar, there's an equation for covariance, and this equation is the covariance of two things, let's call them x and y. This is equal to the expected value of x multiplied by y, subtracted by the expected value of x times the expected value of y. So in our case, we're calculating the covariance of bt, the Brownian motion, and its square, so bt squared. So we have the expected value of bt times bt squared, that's going to be bt cubed, minus the expected value of bt times the expected value of bt squared. So immediately from the properties of Brownian motion, we know that bt, this is going to be normally distributed around a mean of 0 and a variance of t. So because it has a mean of 0, then the expected value is going to be 0. So expected value of bt equals to 0. So now we need to look at that means this term here will get cancelled out to 0. Now we need to look at bt cubed. So remember, bt is going to look something like this. Let's draw it better. So it's a normal distribution with a mean of 0, variance of t. So if we cube this, then both the positive side and the negative side are going to be cubed. So after cubing, it'll look something like this. Both the positive and negative sides increase by the same amount. So the expected value is still going to be 0 because both top half and bottom half changed by the same amount. So the expected value of bt cubed, this is going to be, again, be 0. So that means this term is also 0. So it doesn't matter what the expected value of bt squared is. This is actually going to be equal to t, but calculating that is beyond the scope of this video. It requires some calculus. So the covariance is actually just going to be 0 subtracted by 0, so that is just 0. So the covariance between bt and bt squared is 0. So moving on to the third question, and perhaps the most interesting part, is calculating the stoppage time of a Brownian motion. So calculating the expected stoppage time. So how do we define stoppage time? Well, it's the time it takes for a Brownian motion to reach a certain threshold. So if we draw a diagram here, let's say we have a upper bound of alpha and a lower bound of negative beta. Let's actually use numbers in this case, so it's easier. So we have a upper bound of 5 and a lower bound of negative 3. So whenever the Brownian motion, it starts at 0, whenever it reaches 5 or reaches negative 3, we're going to stop it right there. So for example, a Brownian motion could look something like this, and it stopped at negative 3. Another one could look something like this, and it stopped at 5. And finally, let's do one more example. It went down, but it went back up, and it stopped at 5. So we want to know how long it takes expectedly for the Brownian motion to reach either 5 or negative 3. So basically, we need to calculate the tau here. So to actually solve this question, we're going to use a fact that this is a martingale. Again, this is beyond the scope of this video, but we should just know the fact that the expected value of bt squared, b tau squared, is going to be equal to the expected value of tau. So I could cover martingales in a future video, but for this question, we're going to just assume this fact is true. So the expected value of b tau squared is going to be the expected value of tau. So now we're going to calculate the expected stoppage time of a Brownian motion, and instead of 5 and -3, we're going to change those to variables. So we're going to change that to be alpha and -beta. And now we're looking for the expected value of tau, which is how long it takes to reach either alpha or -beta. So starting off with a property of Brownian motions, we know that the expected value of b tau is going to be 0, because b tau is always going to be a normal distribution centered around 0 with a variance of t, or tau. So we know the expected value is 0. Another way to represent expected value is the values times their probabilities. So there's only two possible values at tau, or our stoppage time. This is tau. So the value could either be -beta or it could be alpha. So suppose it's -beta, then we need to multiply -beta by the probability we reach -beta. So p b tau equals -beta. So the other possibility is that we reached alpha. So the expected value is alpha times the probability we reach alpha. So b tau equals to alpha. So this is 0 because this is the expected value of b tau, which is a normal distribution centered around 0. So we know that the probability that of b tau equaling -beta is the same as the probability of b tau equaling alpha, because we either reach one or the other. So we can represent the probability that we reached -beta to be 1 minus the probability we reached alpha. So to write that, -beta times 1 minus the probability we reached alpha. So b tau equals to alpha plus alpha times the probability we reached alpha. So to expand our equation here, let's actually move everything to the right. So to expand our equation here, we have -beta plus, not times, beta times p, probability that we reached alpha, plus alpha times the probability we reached alpha. And this is equal to 0. So now we can isolate the probability we reach alpha to calculate that probability. So the probability here is probability b tau equals to alpha equals to move -beta to the other side, it becomes positive beta over alpha plus beta. So now we also want the probability of b tau reaching -beta. So probability b tau equaling -beta. This is equal to 1 minus the previous one. So 1 minus beta over alpha plus beta. This is equaling alpha over alpha plus beta. So we have this probability and this probability. Now, taking advantage of our equation here, the expected value of tau equals the expected value of b tau squared. Again, this is from a martingale, and we're going to cover that concept in a future video. So what's the expected value of b tau squared? Well, that's just the squared of the expected values. The values are alpha and beta, and -beta. So we're going to square alpha times the probability we actually reached alpha. The probability is going to be beta over alpha plus beta, which is this thing we got from there. So plus, the other alternative is we reach -beta. So -beta squared, because we're squaring b tau, times the probability we actually reach this, which is going to be alpha over alpha plus beta. So to simplify these fractions here, we're going to have alpha squared beta plus beta squared alpha over alpha plus beta. So we can factor out alpha times beta on the top, on the numerator, so alpha times beta, and in the bracket, we have alpha plus beta, divided by the denominator, alpha plus beta. So the numerator and denominator can cancel out here. So all we're left with is alpha times beta. So the expected time, or expected stopping time, tau, is actually just going to be equaling to the values alpha and beta multiplied together. So in our case, if alpha is 5 and negative beta equals to negative 3, then the expected stopping time is going to be 3 times 5, and that is going to be 15. So another question that can arise from the stopping time is, for example, what if we only have one bound? So we know that in the case that we have two bounds, for example, 5 and negative 3, the expected stopping time is going to be 15 time units. However, what if we only have the upper bound? For example, we only have the upper bound of 5. Then the Brownian motion can go down infinitely and potentially never come up. Or if we use the equation that we got, expected value of tau equals to alpha times beta. We can say that the expected negative bound is going to be negative infinity. So this is going to be 5 times infinity, which is infinity. So we have an infinite expected time for tau. So that's it for the introduction to Brownian motion and some questions associated with it. I'll cover some other concepts such as martingales and more stochastic calculus in the videos to come. Thank you guys for watching. Hope you're able to learn something, and I'll see you in the next video.